A controlled form of this energy has now been developed for use in the aircraft industry. The process is called electrochemical machining. It removes metal using an electrical current flowing through a chemical solution. An electrochemical machine holds the tool and workpiece and provides the necessary motion for machining to take place. A power supply, sometimes with a capacity of up to 40,000 amps, provides suitable electrical energy by converting alternating current, the type coming from a wall socket, into the needed direct current. The tool contains the same shape as the surface or its configuration to be produced on the part. This is connected to the negative terminal of the power supply and thus becomes a cathode. In most applications, this cathode is hollow, providing a passageway for electrolyte. The electrolyte is a chemical solution which conducts electricity. A common electrolyte is salt water with 1 pound of salt per gallon of water. The workpiece is attached to the positive terminal of the power supply, becoming an anode. This can be made of any commonly used metal, regardless of hardness. The system also contains a storage tank where clean electrolyte is maintained, pumps to supply the electrolyte to the tool, filters to remove contaminants, and sludge removal equipment, such as a centrifuge or settling tanks. When machining is ready to begin, the electrolyte is pumped into the gap between the cathode and the workpiece. During machining, this gap is only about 5 to 10 thousandths of an inch. The power is then turned on. An electrical circuit is now complete, and the current begins to flow. As a result of the occurring electrochemical activity, small particles of metal are removed from the workpiece and, as they chemically combine with the electrolyte, are converted to sludge. Here is what an actual ECM setup looks like. The machine holds the tool and workpiece and provides the needed motion. Energy is provided by a power supply. The cathode, or tool, attached to the negative terminal of the power supply does the actual work. This one is used to produce pockets in a ring. When the electrolyte is turned on, it begins to flow onto the part, which is attached to the positive terminal. Before machining, the cathode section and anode section are clamped together. The power is then turned on. This causes machining to take place. Included in the system are a storage tank, pumps, filters, and a centrifuge. In most ECM applications, there are two elements that must come under careful control before good machining efficiency and accuracy can be provided. First, the closer the cathode is to the anode, the stronger the current and the faster the metal will be removed. But as machining continues and the gap gets larger, the current becomes smaller and the machining rate decreases. Secondly, most metal is removed directly under the cathode where it is closest to the anode. This electrochemical action is not selective, however. All surfaces of the anode in contact with the electrolyte are affected. Control is accomplished primarily in two ways: by regulating the size of the machining gap and by insulating the cathode. A constant and rapid metal removal rate can be obtained by maintaining a constant high level of current between the anode and cathode. This can be done by moving the cathode toward the anode at the same rate at which the material is being removed, thus keeping the gap relatively constant. In some applications, this is unnecessary and stationary anodes can be used. Undesirable metal removal can be minimized by applying an insulating material called a dielectric to the cathode where needed. This shields part of the machine cavity from the electrochemical action. In many machining operations, the ECM process has qualities that make it more effective than other machining techniques. For one, parts made from hard, tough metals that are difficult to machine by conventional means, like this titanium fuel control lamination and this gear blank, can be ECM'd as readily as parts made from soft metals. And this can be done without wear on the ECM tool. Notice the difference between the used EDM electrode on the left and the used ECM cathode on the right. ECM also has the ability to produce large as well as small, complex contoured surfaces in a single pass of the tool. These configurations on this compressor casing were all ECM'd. In many cases, this can result in significantly faster machining rates than can be achieved with more conventional means. This graph shows comparable rates between ECM at 10,000 amps and conventional milling for producing hard-to-machine shapes in very hard nickel-based superalloys. Furthermore, secondary operations, such as the removal of sharp edges or burrs, or the generation of rounded edges, are unnecessary. The contoured edge on the compressor casing on the left was contour milled, the boss on the right ECM'd. Notice the difference. However, there are significant drawbacks which must be taken into consideration before a decision to use ECM is made. Accuracies normally associated with conventional metal working techniques, such as contour milling, cannot be met. And not all materials ECM alike. Surface textures can vary significantly from one material to another, even when the same machining conditions are used. Special technical knowledge is, therefore, needed in order to develop the proper machining techniques. Still another drawback is that equipment and maintenance costs are very high. A typical machine costs about $250,000. And ECM tools can fail even though they do not experience wear. Foreign material in the gap or a momentary instability in the machining can cause a short circuit, resulting in excessive current between the tool and the workpiece and cause extensive damage to both. Also, failure of the cathode insulation can result in unwanted metal removal. As you can see, ECM is an entirely different process than conventional machining techniques. Instead of a hard tool applying pressure to a workpiece to remove metal, electricity flowing through a chemical solution is used. Machine holds the tool and part and provides the machining motion. Electrical energy is supplied by a power supply. The tool, or cathode, is attached to the negative terminal. The workpiece, or anode, is attached to the positive terminal. Electrolyte, an electrically conductive liquid, flows into the gap between the tool and the workpiece.